Very interesting meeting at the Metropolis. And so my name is Gustavo Dalpian. We had a very small change in the program this afternoon. I was supposed to talk after Professor Eduardo, but Professor Thiago Branquinho is going to talk after Eduardo, and I'm going to talk later on today, okay? So Professor Eduardo Novaes comes from Universidade Federal do ABC, my colleague there. So the floor is yours, Eduardo.
Thank you very much, Gustavo. Can you guys hear me? All right, so thank you very much for your attention. Thank you for the invitation to talk here. It's always a pleasure to meet my friends again. And I want to make an apology because tomorrow I will not be here. So for the speakers, tomorrow I will not be here because I will be teaching the whole day. I'm replacing another professor that has a personal problem, and so I cannot be here. And I'll be a zombie on Friday too, so I'll have to apologize for Friday also. So now, what I would like to discuss today with you, it's a little bit of a change of gears from the first seminars that we had this morning, and it's called the Impurity in the Extended Hofstadter-Hubbard Model. And what is this point? What is the Hofstadter model and why I'm interested in it? So we've been talking about topological systems for quite some time now. For 10, 15 years, it becomes a kind of a fashion to talk about topological systems. And I was driven into this particular kind of research by this paper by Duncan Haldane from 2008. And there you go. And in this particular problem, Duncan Haldane showed an interesting property of topological systems, which is called, he called this entanglement spectrum. So what he was looking at is that we all know that when you have a topological system, and he was looking at fractional quantum Hall effects, you have a boundary state, a border state that goes around. This boundary state goes around, and it's characterized by the kind of topology that you have. So depending on the topological system that you have a different edge state in your quantum Hall state, or even. Sorry about that. That's fine. Thank you. So depending on your topological state, you have a different edge state. And what Haldane was talking in this paper is that, well, if you get a topological insulator, or a topological system, any one, and you put in a sphere, for example, and you put a magnetic monopole, he was talking about topological systems in the context of the quantum Hall effect, and you cut this sphere in half, you can do it. You have the ground state, you can do it, and when you do it, you do the Schmidt decomposition, and the Schmidt decomposition of your system has some parameters here. It's always a positive number, and you can write it as an exponential. So you can understand the Schmidt coefficients as a Hamiltonian, as energy of a Hamiltonian system. So, and he was arguing that these Schmidt coefficients have much more information about the system than the topological entropy of the system. And because from here, you can actually calculate the topological entropy. Well, and so the point that he was trying to make is that, okay, you have this topological entropy, is this entanglement entropy that you calculated now, and you have this topological, you have this entanglement spectrum. And what is this entanglement spectrum? And what he found is that the entanglement spectrum reproduces the low energy physics of the boundary state. And this is not obvious at all. So you cut your system in half, you have no boundaries at all, and then you reproduce this edge state in the middle. But this edge state will come in this particular form with some kind of temperature. And what temperature is this? Because now you cut half of the system, you start with a pure state, and now you have a density matrix to work with. And you have some temperature to understand. So my question here when I start reading this is, does this have any measurable effect? When you are just calculating, you have a system and you just cut it in half, and you calculate this entanglement spectrum, does it have some measurable effect? And in other words, can you probe the topology and understand the topology by measuring things in the system in the bulk? Usually we don't think about this because topological systems are supposed to be protected from small perturbations for local perturbations. And the idea is now is, well, if the wave function of the topological state do have some information that can be probed locally with some impurities, for example. So the idea is that, yes, there are some effects. So this is the result that I'm going to try to show you. And I will try to find ways to argue that it's also possible to identify the kind of entanglement and the kind of topology that you have in your system. This is still a work in progress, but it's going smoothly right now. So let's just start with the Hofstadter model. And it's not this Hofstadter. This is the guy from Big Bang Theory, is this Hofstadter, Douglas Hofstadter. And he created this model when he was doing his PhD thesis. And what is this model? Well, the idea is very simple. You have a magnetic field, and you have a lattice. So it is a discrete version of what you expect for a topological system, for a quantum Hall system. And it's kind of easy to see that you can use the Pyro substitution in the Landau gauge to write the model like this. So you have a square lattice, you have a magnetic field applied to it, and then the particle hops around. And when it hops around, it gets some phases that depend on the magnetic field that you are applying. Right? So it depends on the flux on the plaquette, on each plaquette. Right? So a very famous limit here is the pi flux, where you have the maximum amount of flux in each plaquette. And this is a very simple model, and it's actually the simplest model that will emulate the quantum Hall state. Okay. So do we have experimental realizations of this? Yes, we do. So this is using atoms, and you have a lattice here, and you have the hopping assisted by lasers that gives this effective magnetic field. And so you can reproduce the Hofstadter model in this system. Well, why we never talk about it when we teach quantum Hall effect? We never talk about it because the magnetic fields, in order to produce synchrotron orbits with the size of the lattice parameters, are huge, and so we don't talk about it. So it's always ineffective. The lattice is never thought about. So to discuss this, we need to go to ion traps, to some other kind of idea, not a simple magnetic field. But as a theoretical model, it's a very interesting model. And recently, it also been seen in Moire's superlattice in graphene and other materials. So the whole point of this model is that it's the simplest model that you can try to study incommensurate to commensurate transitions. Because we have two lattices competing with each other. You have the magnetic lattice, and you also have the real lattice that the fermions are moving around. So you can study the transition from commensuration to incommensuration by changing the magnetic field in your theoretical parameters, right? So this kind of ideas and problems brought back the Hofstadter problem. And what I'm going to discuss here is also the interplay of the Hofstadter model when you introduce interactions. So when you introduce interactions in your system, in a square lattice, you introduce a Hubbard kind of interaction in your model, and you expect at half filling a Mott insulator to a semi-metal transition. And as you introduce the Hubbard U. But as you increase the magnetic field, you reduce the effect of the interactions, and your transition from semi-metal to Mott insulator changes. So as far as I know, nobody knows this exact phase diagram. So this is just a line that I draw there. You have two limits. You have the Mott insulator and the semi-metal, But this paper, this Nature Communication here, say that they are going to do this as a future work, right? So the point here is that now I want to address is we do have these local interactions, these Hubbard interactions. You have the magnetic field and the lattice frustration that is introduced with that. And we, in principle, can construct a topological model. Can we probe this with a local probe with an impurity dynamics? And so in order to do that, the first things, I want to create a real topological insulator. So in order to do that, in addition to the usual Hofstadter term, which is nearest neighbor hopping, I have to introduce next nearest neighbor hopping. And the reason is that when you only have the Hofstadter model and the applied flux regime, you have your Dirac cones. And that's why you have a semi-metal. But when you introduce the next nearest neighborhood hopping, then you open a gap, and the gap is proportional to these hopping terms of the diagonals, okay? And so this is exactly what you expect for a topological insulator. So is this a reasonable model? Yes. And in fact, it's kind of interesting that it's probably doable if you have two square lattices and a bilayer two square lattices that are overlaying each other, right, in a more like pattern. And if you have an inversion of your bands, then maybe you don't even have to have a very large magnetic field in order to do this. So it's a very reasonable model to be done in the lab, right? So is this a topological insulator? Yes, it is. You can calculate the Berry curvature, and the chair number turns out to be ±1 for each one of your bands. So it's really a topological insulator. And what about the boundary states? Well, the boundary states, you can also calculate exactly. And in order to do that, you just Fourier transform in the one direction that you keep infinite, and in the other direction, you just put a boundary. And when you do that, you end up with nice exponential decay functions, which depend on the momenta that you have in the infinite direction. And this is the real part of your boundary fermions. And in the end of the day, you have a boundary Hamiltonian, which is just chiral boundary states, just like you expect from the usual quantum Hall, integer quantum Hall effect, right? So this is following exactly the recipe to construct your topological insulator. You have a boundary state which has this Hamiltonian in the boundary at low energies. So what about the entanglement spectrum? Well, again, just following Haldane, but now with your finite discrete system, and you put it on a sphere, and you cut the space in half. Do your Schmidt decomposition. And when you do your Schmidt decomposition and trace half of your sphere, half of your system, right? So I'm cutting it around here. You end up with a reduced density matrix when you have the Schmidt coefficients, and you can write it as an exponential. So this is your entanglement spectrum. So the reduced density matrix can be written in this form. And what are these energies, and what is the temperature that comes here? Well, the temperature that comes here is actually proportional to the gap of the system. So what you are finding is that when you calculate the reduced density matrix of your system, you find this entanglement spectrum, and it is the temperature that shows up is proportional to the gap that you have. You can calculate this exactly using the correlation functions of the non-interacting system. And what is the result? Well, the result is exactly what Haldane has pointed out. You have free chiral fermions in your boundary, and you have a temperature here, which is proportional to T, which is the hopping term of the diagonal of the square, right? So this is a very interesting model, and the idea is that you reproduce exactly with analytical calculations everything that you know about the quantum Hall state, right? So I can now bosonize, because I did this in my childhood, when I was studying my PhD. And you bosonize your system, and the free fermions are now chiral bosons. Right? So you have your chiral bosons, and you have a temperature here, which I'm going to call temperature of entanglement, which comes out as proportional to the gap of your topological system. Right? So now I want to introduce the interactions. So you can do that. You can introduce, and in the end of the day, the final result is that you introduce a Luttinger parameter in your chiral system. So these are only forward scattering terms that you have, and this is the chiral model that you expect for the quantum Hall state, for the edge state of the quantum Hall state. And G is, in the quantum Hall, is related to the filling of the Hall state, and here it comes out as a term that comes from the forward Hubbard interactions. Right? This is exactly what was calculated using conformal field theory by Ludwig and collaborators a long time ago. So here he has conformal, he has a topological system in general, but he was focusing again on quantum Hall states, and he's cutting the system in half and calculated the entanglement entropy, and he found exactly that. So you have a Luttinger liquid, chiral Luttinger liquid with a different Luttinger parameter depending on your interactions, right? So now I'm going to my point. Can we probe the system with a local impurity and find something interesting? Well, the idea comes from the Unruh effect. The Unruh effect is a relativistic theory, a quantum field theory in a relativistic environment. And when you have an accelerated observer, this observer is casually cut from half of your space-time. So this is a natural way to describe the system as tracing half of your space-time environment. And when you do that, then you define the Unruh temperature. So when people study this model, well, usually they discuss with the DeWitt detector. So the accelerated observer sees a certain temperature that it comes from cutting half of space-time, and he measured this temperature with a detector, which is a local two-level system that follows a geodesic accelerated curve along space-time. So that's the idea. You have an impurity, and you try to solve the dynamics of this impurity in your reduced space-time. Right? So that's the motivation to now introduce a resonant level in my model. So I have the Hofstadter model, I included the Hubbard model, and now I'm adding to it an impurity level, a resonant level. So it's a flat state here in the middle of my gap initially. Right? So I have an impurity, and I put it there. I have a resonant level model there. And I add to it, so I have the lattice, the pi flux lattice, the Hubbard term, and I add to it a hopping in and out of this local levels that I will call D. Okay. So now we do that, and I'm going to trace half of the system. Right? So I have the impurity, and I'm cutting it, but my cut passes through the impurity. So what happens is that in addition to my bosonic chiral fields, which comes from the edge state, from having cut the system in half, I also have the dynamics from the two-level system. And this is exactly what you would expect that you find if you study the Kondo problem. So this is a resonant level model, or the dissipative two-level system. You can call many names, but the beast is the same. And it has been studied for a very, very long time. So you can do the renormalization group now, because now I have a bosonic theory, which has a Luttinger parameter, and now I have my resonant level model hopping in and out of the bosonic theory. And you can do the renormalization group. Why I'm doing the renormalization group? Because I want to know what happens when you introduce the interactions. Without the interactions, with G equals 1, I can solve it exactly, and I'll solve in a moment. But if I want to know what happens when I introduce the interactions, I have to do something better than just perturbation theory. And the reason for that is because when you have attractive interactions in your Hubbard model, you are flowing in this region to the Kondo regime. And here is the exactly solvable model when your ressonant level model doesn't, you don't have any interactions at all. And repulsive interactions, you enter in another regime called the perturbative regime. So you have your RG equations. You have now, you can change the flows of your, you can study the flows of your equations, the various regimes. But you still remember that I'm talking about an impurity in a reduced system which has a certain temperature, my entangled temperature. So what I'm going to do is that I'm going to follow the RG flow until a certain point, until I found the energy scale of the entanglement temperature. At that point, you cut the RG flow and you renormalize, you find what are the energy scales at that point. So this is a very standard procedure, right? When you have an insulator and you are doing, or when your system opens a gap, you follow your RG equations until you find the breaking point where your gap is open. Or when you have a temperature, you do the RG at 0 temperature, and then you stop the RG flow when you find the temperature that you are at. So this is that you have. So this is a very standard procedure, and you follow the RG equations until you find the renormalized constants. So what I'm going to study, and I could write down many things to look at, is the probability that you have your single levels there in the middle of the gap populated and remains populated after a while. So I can relate this to several different forms of experimental information that comes, right? So photo emission and so on and so forth. So in the traditional two-level system, this will be the Rabi oscillations of your system, right? So the first thing is to calculate with no interaction. So I take out the Hubbard model. And this is an exactly solvable model. And you have that this probability is exponential with the bandwidth and the square of the hopping parameter. And t here is the time. And the thing is that it's a well-known fact that this probability, or this Rabi oscillations, will not depend on the temperature for a no-interacting system, right? So it's so since my temperature is this entanglement temperature, it doesn't depend on the gap. Only on the hybridization lambda between the band and the local level. But now, when you do have interactions, your renormalization changes, and you have to do some tricks. And here is the non-interacting blip approximation. When you dress up with interactions, the history of your two-level system. And you find out that in the end of the day, your probability do depend on the parameters that you have, but also on the entanglement temperature and the interactions, right? So in the end, you find that although you are in the middle of your insulator, you find a signature of the topological and of the topological nature of the system and the interactions in this probability that can be related to photo emission or other things that you would like to study, right? So what are the main conclusions at this point? The first one is that, okay, entanglement, spectrum of entanglement can give you a lot of information of your system, and more than just the entropy of your system. The second thing is that you can probe the topological nature and the topological signatures of things without having to look at the boundaries. So this is something that usually people do. Well, the simplest thing that you can do is you have your topological insulator, you measure the current that is passing on the edge state. That's something that you could do. But you never talk about the bulk because the bulk is supposedly inert. It's just an insulator there, right? But now I can tell you that, well, it's not exactly an insulator in the normal sense. Because when you have this entanglement of entropy and this entanglement spectrum, you do have a signature of these boundary states in the bulk. So you have a bunch of impurities in your system, and they will respond to this, to some external driven force in a very peculiar way even though you are in this insulator state, right? So this is an interesting point. The only difference is that you have a finite temperature to work with. You have to work at finite temperatures, but it's not a real temperature, it's just the size of the gap, right? And in our example, we also found here that when you introduce the interactions, you can qualitatively change the behavior of this response of these interactions, of these local probes to your system. So it's another way to find out what are the correlations inside the topological insulator. So the interplay between interactions and topological insulators and topological materials is still a very open question. And so this is a very interesting point to move forward. So thank you very much. I hope you guys found it interesting.
Okay, the talk is open for questions. I actually have a question, Eduardo.
Yeah.
So you said that the temperature of entanglement is proportional to the gap of the system. So
yeah.
I understand that you increase the gap, you increase entanglement. So can you
elaborate
a little bit on that? So what is the physical meaning of?
It's exactly the opposite. When you increase the when you increase the gap, you localize the system.
No, that's okay.
So it's exactly the opposite.
That's okay. That's very good. So another question. So can you tune the position of this level, the impurity level, because you placed it exactly in the middle of the band gap? Is there a reason for that?
No, it's just because
make it shallow, for instance.
Yeah, you can. You can. As a theoretician, you can put it anywhere, right? But the idea to put it in zero is that because when it's not localized, well, it's not hybridized with the band, right? That's where you expect it to be.
Yeah, so that's what I was thinking, whether shallow sometimes have different properties. Okay, I understand that. You can. There is a question over there, so let me take the microphone over.
Thank you, Professor. Very nice talk.
Thank you.
It's a naive question. You said that you use renormalization group because perturbation theory is not good for this problem. I was thinking you expect some, what's the name, screening of the impurity, like in Kondo.
Oh yeah,
Kondo
so
model.
we are exactly in this Kondo regime, right? When you have, what I was trying, I probably flashed too much this, is that you have, when you have these attractive interactions between your fermions, you are exactly in this Kondo regime for this two-level system. So you would go to this screening. So you have a competition between the Kondo temperature and also the entanglement temperature that I was talking about. So if the Kondo temperature is higher than the entanglement entropy, your two-level system will simply disappear. You're not going to see it anywhere, right? Because that's what the Kondo does. It's completely screen your system out. So you do not have a local system anymore. It's completely dissolved into the band, right? But the regime that I was talking about, and thank you for the question, is exactly that you have a Kondo temperature, but your entanglement temperature is higher than the Kondo temperature. So you cut the flow of RG before you reach the Kondo temperature, and that's what happens. This is a very standard procedure when you have a finite temperature. You're working the Kondo model in a finite temperature.
Thank you.
Okay. More questions?
I don't know if I got it right, but you work for all the Hofstadter spectra is a function of the magnetic field.
Yes.
So you work for only one field.
For one field, for the pi flux. For the pi flux, because that's the simplest one where you only have to solve 2x2 matrices. If you go to other fieldings, right, so you have a more complicated band structure, and you can do that. The most interesting problem that people are really trying to address now is when you have incommensurabilities, right? And your magnetic lattice do not sit well with your physical lattice. Exactly. I didn't work with that. And that's when you have the fractal structure.
Because when you change the magnetic field, you are changing the magnetic lane and the interaction between the edges and the impurity.
And you're going to change the edge, exactly.
Okay, so
the
you
edge
change the
state.
interaction and
Yes.
probably use, okay.
Yes.
More questions?
I have a question. So this idea that, I mean, in principle, the topology is contained inside the Hamiltonian, so you don't really need an edge state to, the problem is measuring it.
The
right?
problem is measuring
Yeah.
it, exactly.
So this is a very nice idea, but the whole idea here should work also for a non-interacting system then, because you should be able to probe the Hamiltonian in the same way.
Yeah,
right?
well, in principle, is in the entanglement spectrum, right? So if you measure the entanglement spectrum, then you're going to find information about your system. But as I was trying to show here, in the non-interacting system, it doesn't depend on the size of the gap, which is a kind of an important information for your topological system.
Right.
So when I found that, this is a very well-known fact that the resonant level model doesn't depend on the temperature or the size of the gap or the temperature that you're working with in this resonant level model. In the non-interacting system, you do the calculations, and it's a Paco Guinea paper from '82. It's an appendix there, and it comes out, and it's a result. And when I found that, well, that's funny, right? Because I know that I have this spectrum there, but it is insensible to the gap. And how can I make it sensible to the gap so I can measure the gap, well, or understand the gap in these local properties? Right? And the way to do that was to introduce the interaction. So that was the main reason. There is another point that reason that I'm trying to understand this whole business between topology and impurities is because sometimes you say, well, you have a topological protected system, and I can do small deformations in it and nothing happens. And you try to do quantum computations on these systems. That's fine. And on the other hand, you also have these NV centers, right? And well, say, well, okay, this is in the middle of a huge gap. It's extremely protected from everything that is coming from outer space because you are in the middle of the gap within your NV center. Is it really true if you have a topological system? Does it being in a gap really, or your local system prevents you from the coherence, for example? And what I'm trying to say is, not true. There are some limits to this argument.
Okay. Any more questions? Oh, if not, let's thank Eduardo again. Thank you, Eduardo.
Thank you very much.
Okay. Now we